Alright guys, how's it going? Today we'll be discussing chapter 14, electromagnetic energy. And as you guys can see here specifically, we'll be focusing on electromagnetic waves. Here you can see that some waves transfer energy using the motion of matter. And here you can see examples of that in parentheses, both sound and ocean waves. Sound waves transfer energy through the air and the air particles in the air, and here you also see that ocean waves will transfer their energy through the matter found in the water molecules and the different things found in ocean waves. So other waves transfer energy without requiring matter. Here you see an example in the parentheses, a vacuum. Possibly you could imagine light, which is an electromagnetic wave, transferring its energy without matter. There's no matter there. It's just radiating and traveling through space in a vacuum. It does not require a medium of matter to travel through outer space. Here you also see that electromagnetic waves. You guys need to be familiar with those. You see the X-rays, light, and microwaves. These are all examples, and there are many other examples of electromagnetic waves. We also see here that the entire frequency continuum of the electromagnetic waves is the electromagnetic spectrum. You must know the electromagnetic spectrum in order, and you need to see page 300, figure 14-2. Here you will see a picture of the electromagnetic spectrum. You guys do need to know this in order. You can do it from top, starting at gamma rays, down to the bottom of long wave radio waves, or you can start at the bottom, long wave radio, and go up to the top gamma rays. But you guys need to know them in order. Me and Miss Arthur will be checking, and you will have a quiz on that. So be prepared for that in the coming days. Moving on, we see the properties of electromagnetic waves. There are 1, 2, 3, 4, 5 of them. You see the waveform is a property. Speed is a property of electromagnetic waves. Frequency and wavelength are corresponding. Photons are also important properties. And you see lastly that intensity and energy are corresponding properties of electromagnetic waves. We will begin here with the waveform. The waveform is oscillations in two fields, the magnetic and the electric fields, and they are oriented perpendicular to each other. We have a picture here of the wavelength waveform. You see highlighted in red is the electrical field, and magnetic field is blue in B. As you can see, they are perpendicular to each other, and this is just you need to have a firm understanding that this is how electromagnetic waves operate. They travel in waveforms like this. They both have both an electric field and the magnetic field that are perpendicular to each other as they travel. Speed is also a very important aspect of wavelengths. They are very fast. Of electromagnetic waves, they are very fast. As you see, the speed of light, represented by the variable c, the speed of light in a vacuum is exactly 299,792,458 meters per second. And do keep in mind that this isn't a vacuum, so there is no matter to slow it down. Memorize the speed of light. You guys must memorize this speed of light here. 3.0 times 10 to the 8th power meters per second. You guys must know that. It will be on a quiz, I'm sure. And so mark that, remember that, and be sure to know that for the quiz. Here you see, as I said, in a vacuum, it's the top number up there, but it will be slower when moving through matter, which will hinder the motion of the waves. We also see here that frequency and wavelength are important corresponding properties of electromagnetic waves. You see this formula here, C equals F times that symbol there. C is the speed of electromagnetic waves in a vacuum, as we've already discussed. And you must put that in meters per second. We will not be working any problems, but you guys need to be mindful of the units that you must put these in. F is the frequency of the wave, which is measured in hertz, and that symbol there is the wavelength, which is measured in meters again. Moving on, we see that frequency and wavelength are inversely proportional. Higher frequency waves have shorter wavelengths, and vice versa. A person with a high-pitched voice will emit sound waves that are much shorter in frequency or in wavelength than the somebody with a voice that's deeper. Deeper voices and deeper sounds will have much higher wavelengths, and you just need to remember this. You can look up pictures to help you understand the inverse proportional relationship between frequency and wavelength. Moving on here, we see that the photon as an important aspect of electromagnetic waves. Here we see that a man named Huygens, he was a scientist. He did a lot of experimentation with light, and he found that light acts as a wave. And this was a very important discovery and theory that he had. And for a long time, it was just accepted that this was it. But some other scientists, as you see on their second point, they found after a lot of experimentation that light sometimes acts as a particle. And this was confusing to many, but Albert Einstein, being the genius that he was, came up with the wave bundle theory, and he proposed that light sometimes acts as a wave and as a particle, and he developed this theory that all electromagnetic energy is transported as photons, or these small packets of energy. And you need to know that term photon, a small packet of electromagnetic energy. Here you see that intensity and energy are also important properties of electromagnetic waves. The power and intensity are proportional to the square of the amplitude, and that is in mechanical waves. You can measure the amplitude of mechanical waves, which are waves of motion. However, amplitude of an electromagnetic wave cannot be measured directly because there is no matter that can be measured. Whereas you can measure the amplitude of a sound wave or a ocean wave because of the matter that's being moved. But in an electromagnetic wave such as light, you cannot measure the amplitude of the wave because there's no matter to be measured. We see also that Planck's constant is an important aspect of electromagnetic waves. The significance of Planck's constant, as you see here in this context, is that radiation, such as light, is emitted, transmitted, and absorbed into discrete energy packets or quanta. Mark that term in your mind. You need to know that. Write it down. Do what you have to remember that, because that is a very important term. It is determined, these quanta is determined by the frequency of the radiation and the value of Planck's constant. The important thing to remember about quanta is that Albert Einstein found that the quanta and photons are basically the same thing. It's just another term for this, the same thing pretty much. So you guys just need to understand that a quanta is basically a photon. Photon is basically a quanta. It's a discrete energy packet, or that is used to transfer electromagnetic energy. Continuing with Planck's constant, we see the formula here that uses Planck's constant. It measures the energy of a photon. You see E is a symbol for the energy of the photon. H is Planck's constant, which is a very small value. I think it's like 10 to the negative 34th power. It's very small. It measures, the energy of a photon, as you see, which is very small. And F is symbolizing the frequency of the electromagnetic waves. Here we see that electromagnetic wave phenomena it does exist, and there are things that are characteristic of electromagnetic waves. Electromagnetic waves can bend or refract. You see this in light, especially as you see the speed changes in the speed of the electromagnetic wave will change depending on the material that it's traveling through. You see this especially with light, as I said. You see it as light travels through the atmosphere and it goes into like a glass bottle or a glass cup or something. The light will refract or bend in the cup, and it will look as if it's like just going a different direction all of a sudden, and that is a phenomena of electromagnetic waves, specifically light, as you see. in that example. Here we learned the difference between constructive and destructive waves. I have a picture for you down there in the bottom, a little diagram. As you can see, the constructive waves amplify each other. You can see that the highest point and the lowest point are in the same place. The crest and the trough are in the same place, and this constructive wave will actually amplify each other, making the wavelength greater, as you can see. And moving down to the bottom, you see the destructive waves. They will actually cancel each other, resulting in no wavelength, dependent upon the wavelengths of the respective canceling waves there, the interfering waves. If one is greater, it might not cancel it all the way. But there you see in this example that it cancels it completely and actually hinders the wavelength. As you can see, the example of a destructive wave is noise canceling headphones. They actually use interfering waves to cancel the noise, the wavelengths of the sound coming in the headphones. So that's how they work, and I encourage you to study that further. If you need any further explanation, ask me or Miss Arthur, and we will offer you further definition of that. The last thing we see here is the electromagnetic wave. Characterize the Doppler effect. This Doppler effect is something that you experience all the time. You just may not know the name for it. The best example that I can give is an ambulance. If you're standing still on a sidewalk and an ambulance goes by, if you're standing still and you do not move and the ambulance is far away, you'll hear it, and it will be one pitch. And as it gets closer to you, the pitch will increase. It will get higher. It will be a higher pitch, higher frequency, and as it goes away from you, the pitch will begin to descend, and it will be a much lower frequency than it was before. And the pitch actually never changes on the ambulance, but you hear a change in pitch because of the motion of the ambulance. It's called the Doppler effect because there's no actual change in pitch. It just appears that there is. And so that is called the Doppler effect. Mark that, know that. Look up further information on that if you need further explanation. Here you see the gravity of massive stellar objects or objects with large gravitational pulls, gravitational fields. These objects can bend electromagnetic waves such as light, and this term of the bending is called gravitational lensing. It focuses the light around the edges, and it makes it look more focused than it would if the object was not bending the electromagnetic waves. This was actually an unexpected prediction by Albert Einstein. Albert Einstein predicted this in his theory of relativity, that gravity would bend electromagnetic waves. And like you see here at the bottom, it was unexpected because electromagnetic waves do not have mass, and therefore gravity should not be able to bend the light waves because there's no mass for it to act upon. And Albert Einstein, being the genius that he was, predicted that and found that to be true, and it has greatly benefited our understanding of the world around us and the universe in all its many mysteries. And so that will be all that we see today. We talk about today in our discussion of this lesson. In the next lesson, we'll begin our discussion further discussing the electromagnetic spectrum.